Okay, so let us start today's session. Okay, ionization constant of a weak bases. So weak base like MOH, that will give OH negative and M plus, and if you calculate its Kb, that is dissociation constant of weak base, it is concentration of M plus, concentration of OH negative divided by concentration of MOH. And if alpha is degree of dissociation, then change in concentration is C alpha, because see we have MOH to give M plus and OH negative. If solution is means it is as it is a weak base, alpha is very less than 1, so 1 minus alpha can be taken as 1. So in this way alpha comes out to be square root of Kb upon C, or Kb is equal to C alpha square. So in this way OH negative ion concentration is C alpha, so that comes out to be square root of Kb upon C into C outside, so it becomes OH negative is under root Kb into C, and from here we can calculate POH, that is half of pKb minus log C, because we take negative log on both sides, and pH is 14 minus POH. So see this question, it is pH of 0.04 molar hydrazine solution is 9.7. So what is its ionization constant, or we can say dissociation constant, Kb and pKb. So again we start with hydrazine H2O to give NH2 NH3 plus OH negative, and H plus sign is anti-log of minus pH, so H plus is anti-log of minus 9.7, so it can be written as anti-log of 10 bar 0.3, because it is written as minus 9 minus 0.7, that is plus 1 minus 1, because this part should be, decimal part should be positive. So in this way it can be written as 10 bar 0.3, and 10 bar is 10 raised to power minus 10, and anti-log of 0.3, that is 1.67. So in this way this is H plus concentration. So here from this expression OH negative ion is equal to Kw by H plus, because ionic product of water is H plus ion concentration into OH negative ion concentration, and therefore OH negative ion concentration is equal to value of Kw divided by, as it is not mentioned at which temperature, so we consider it as 25 degree Celsius. So Kw at 25 degrees Celsius it is 10 raised to power minus 14, and H plus ion concentration is 1.67 into 10 raised to power minus 10, and therefore OH negative ion concentration we get. Now OH negative ion concentration and hydrazinium ion concentration is same, because this was the relation NH2 plus H2O to give NH2 NH3 plus OH negative. C 0 0. So if it is C minus X, it is X X. That's why concentration of OH negative and hydrazinium ion concentration is same. So we calculate OH negative ion concentration from pH, and therefore same is the concentration of hydrazinium ion, and this hydrazine concentration is given initially, that is 0.04. It is 0.04, so it should be 0.04. I hope answer is correct. 5.98 twice into 10 raised to power minus 10 divided by 4 into 10 raised to power minus 2. What is the value? Just calculated 5.98 into 5.98 divided by 4. So it is 8.96 into 10 raised to power minus 8 actually. So KB, PKB is minus log of KB. So PKB is minus log of 8.96 into 10 raised to power minus 8. So it is 8 minus log of 8.96. So 8.96, take it as 9. So what is the value of log 9? Log 9 is equal to log 3 raised to power 2. That is 2 log 3. That is 2 into 0. What is the value of log 3? It is 0.477. So it comes out to be 2 into 0.477. So it is 0.954. So 8 minus, so that it comes out to be 7 point, instead of 6.04 it is 7.04, because concentration is 0.04 and here calculation is made according to 0.004. So in this way you can calculate KB and PKB. Yes. Water, but actually water is in excess. So, and it is a pure liquid. So pure liquid and pure solids are not taken into account while calculating dissociation constants. Now for a conjugate acid base pair, if Ka is dissociation constant of acid and Kb is dissociation constant of base. So what is the relation between Ka and Kb? That is Ka into Kb is equal to Kw. See, it is like this. Ha, in the presence of water, it gives H plus ion, or we can say H3O plus ion, A negative. So Ka equal to H3O plus ion concentration, A negative concentration divided by Ha concentration. And Kb, this is conjugate base. Ha is acid and A negative is its conjugate base. So in this case it gives Ha plus OH negative. So Kb is equal to Ha concentration, OH negative ion concentration divided by A negative ion concentration, and H2O is pure liquid, so that is not appearing. So if we multiply Ka and Kb, what will we get? See, Ha, A negative cancel. So it is H3O plus concentration into OH negative ion concentration, and that is equal to Kw. This is ionic product of water. So Ka into Kb is equal to Kw, and pKa plus pKb equal to pKw, or we can say 14. This is for acid and its conjugate base. If Ka is dissociation constant of acid and Kb is dissociation constant of its conjugate base, then Ka into Kb equal to Kw. That is ionic product of water. So like this is the question, 0.1 molar aqueous solution of a weak monobasic acid has pH 2.0. So what is pKa of this acid? So from pH first, we calculate H plus ion concentration. So tell me, if pH is 2, what is the concentration of H plus ions? Yes, it is anti-log of -2, or we can say it is simply 10 raised to power -2 molar, because anti-log of the number is 10 raised to power the same number. So anti-log of -2, that is 10 raised to power -2, and therefore H plus concentration is 10 raised to power -2 molar. Now this is, let us say, weak monobasic acid is Ha. That will give H plus ion concentration plus A negative ion concentration. So you know Ka is equal to H3O plus ion concentration, A negative ion concentration divided by Ha concentration. So as it is 0.1, H3O plus ion concentration is equal to A negative ion concentration. Just solve it. What is Ka, and then calculate pKa. Yes, actually, see, if you do, see, actually this is the relation Ha plus H2O to give H plus, H3O plus and A negative. If its concentration is C, it is 0, 0. And if alpha is degree of dissociation is C into C minus C alpha, or we can write it as simply C minus X, and it is equal to X and X. X we have. Now solve it. Or C minus, it can be written as C minus C alpha. So Ka equal to C alpha into C alpha upon C 1 minus alpha. So it is C alpha square upon 1 minus alpha. Here I am not neglecting alpha, because H plus ion concentration is 10 raised to power minus 2 and HA concentration is 10 raised to power minus 1. If H plus concentration comes out to be like 10 raised to power minus 6, minus 5, that means it is far less than HA, then we can neglect. But here H plus HA concentration is only 0.1 and H plus ion concentration is 0.01. So what is alpha from here? C alpha is 10 raised to power minus 2. So alpha is 10 raised to power minus 2 upon C, that is 10 raised to power minus 2 upon 10 raised to power minus 1, that is 0.1. So alpha is 0.1. So in this way, Ka equal to C alpha square over 1 minus alpha, that is 0.1 into 0.1 raised to power 2 divided by 1 minus 0.1. So value is 10 raised to power minus 3 divided by 0.9. So that implies it is 10 upon 9 into 10 raised to power minus 3. So almost 1.1 into 10 raised to power minus 3. So pKa equal to minus log of Ka, that is minus log of 1.1 into 10 raised to power minus 3. So it is minus log of 1.1 plus 3. So 3 minus log 1.1. What is the value of log 11? .04, right? So it is 0.104 or 1.04. So 1.1 it is 104, right? 0.104. So it is very close to 2.9. So this is pKa. Now tell me, volume of water in ml required to be added to 100 ml of solution, 0.1 molar weak acid at 25 degrees Celsius to double its degree of dissociation. Give Ka is given. Yes, beta. First of all, say what is alpha? Alpha is under root Ka upon C. This is Ostwald dilution law. We have discussed it in the previous class that alpha is equal to under root Ka upon C for weak acids. So in this way, if alpha is under root Ka upon C, so let us say alpha 1 is Ka upon C, and what is alpha 2? Let us say this is concentration C1 and this is concentration C2. Ka remains same. Ka does not change with dilution. Ka value remains same. So alpha 1 by alpha 2, that is equal to under root C2 by C1, or we can say alpha 1 by alpha 2 square equal to C2 by C1. And we have to calculate volume of water required to be added to double its degree of dissociation. So alpha 1 and alpha 2, these are the degree of dissociations. This is present solution and this is diluted solution. So we have to confirm that alpha 2 should be equal to 2 alpha 1. So alpha 2 equal to 2 alpha 1 means alpha 1 by alpha 2 equal to 1 by 2. So it is equal to C2 by C1 is equal to 1 by 2 raised to power 2, that is 1 by 4. That implies C2 concentration is 1/4 of the initial concentration. So initial concentration is given to you. What is initial concentration? 0.1 and its volume is 100. Now concentration is 0.1 by 4. Now we have to calculate the volume. So just we apply M1 V1 equal to M2 V2 because it is a dilution formula only now. Initial concentration is 0.1, volume is 100. We have started with 100 ml. Now its concentration is 0.14 into volume. So volume comes out to be 400 ml. That means initial volume was 100 ml and now final volume is 400 ml, and therefore volume of water added means extra water added, because initially it was 100 ml, now it is 400 ml. So how much water is added? We have added 300 ml of water. So volume of water added or required to be added to 100 ml of 0.1 molar weak acid to double its degree of dissociation is 300 ml. Now polybasic, yes. Beta 1, actually if we talk about weak acid, then 1 minus alpha can never be equal to, alpha is 1 for strong acid. Actually what is alpha? Alpha is number of moles or number of molecules undergoing dissociation divided by total number of molecules. So total number of molecules can never be, number of molecules undergoing dissociation can never be greater than total number of molecules. So alpha is always less than 1. Alpha is always less than 1 for weak acids. So how do we get 1 minus alpha as? It can be 1 for weak acids. It can never be equal to alpha actually, because alpha, maximum value of alpha, if alpha is 1, then this formula is not applicable. This formula is applicable only for weak acids. Ostwald dilution law is for weak acids only, because there is no need to calculate alpha if it is a strong acid. If it is a strong acid, alpha is 1 only. So we start with alpha 1. Okay, it is for, yes, sorry. Yes, here we are taking it, see, Ka equal to C alpha square upon 1 minus alpha. We are taking 1 minus alpha is 1 here. That's why Ka is C alpha square. In most of the cases we take it as 1, but if Ka value is less than 5 into 10 raised per minus 2, means 5%, then alpha is considered. In most of the cases, Ka value is means 5 into 10 raised per minus 2, means 5% we can say. Then we are not, here see, Ka is 1.8 into 10 raised per minus 5. That means it is a very weak acid. So here we can take it as 1 minus alpha as 1. Okay. Now polybasic acids. Polybasic acid means which can give more than 1 H plus ions. So acids which have more than 1 ionizable protons per molecule, that is called polybasic acid. For example, we have carbonic acid, and it is always true that Ka1 is always greater than Ka2. Why is it so? Because once H plus ion is removed from a neutral molecule, we get anion, and from anion to remove a cation is difficult. We cannot remove cation from an anion. That's why Ka1 is greater than Ka2. It is always true, because first H plus ion is removed from neutral molecule and second H plus ion is removed from anion. So there is an electrostatic force of attraction between cation and anion. That's why lower ionization constant, that is primary ionization constant, is always greater than secondary. Secondary is greater than tertiary if it is there. See, in this case there are only 2 H plus ion, so it is dibasic, and Ka1 is greater than Ka2. And what are the factors which affect the acid strength? So first is strength and polarity of the bond. Both will affect. If it is strong bond, it is difficult to break. If it is more polar, again it is difficult to break. So dissociation energy required to dissociate the bond is proportional to strength of the bond. It is also proportional to polarity of the bond. Now if we go down the group, then bond strength is more important factor. That means size dominates. So if we go down the group, size increases, and as size increases, bond strength decreases, because bond length increases. So as atomic size increases, bond strength decreases, and therefore it is easier to get H plus ion. Therefore, acidic strength increases. So HI is stronger acid than HBr. HBr is stronger than HCl and HCl is stronger than HF. As we go down the group, acidic strength of hydrogen halides increases. In a period, strength depends upon polarity. Polarity becomes more important. So as we go along the series, bond polarity increases because atom becomes more and more electronegative, and therefore acidic strength increases. So for hydrogen containing compounds, means hydrides, along the period as well as down the group, acidic strength increases. Along the period due to increase in polarity, down the group due to decrease in bond strength. Now common ion effect we have already discussed. Common ion effect means when we have a ion common to the already present substance. Like we have acetic acid. Acetic acid is a weak acid. It gives H plus ion and acetate ion. So we can write it as like this. Now in this, if we add a compound which has acetate ion or H plus ion, so out of acetate and H plus, they are common to the already existing acid, so that will shift the equilibrium backward because one of the product is increased. See, HAC. So it is in equilibrium. Let us say we add HCl in it. Already we have acetic acid and we add HCl. HCl is a strong acid. So strong acid that will give H plus and Cl negative. So this H plus ion, now it is common. Because of the presence of this common ion, concentration of H plus ion in the solution increases, and therefore this equilibrium, according to Lech-Tellier's principle, when one of the product is increased, equilibrium shifts backward, and therefore dissociation of weak acid is suppressed. And there is one more effect that is called odd ion effect. That is not covered by NCERT, but it is common that if we have acetic acid and we add sodium hydroxide in it, obviously it is a neutralization reaction, but what happened to equilibrium? See, when we have sodium hydroxide, it is anti to H plus ion. OH negative ion combined with H plus ion to give H2O. So there is a decrease in the concentration of the product, one of the product in the equilibrium. So equilibrium shifts forward. That is called odd ion effect. So say in this case, strength of acid increases. Due to the presence of odd ion, strength of weak acid increases. But if we add common ion, then acidic strength further decreases. It is suppressed because of the presence of common ion. So what are the application? It is used in controlling H plus ion concentration in buffer solution. So we will study it in detail in buffer solutions. Common ion effect is used in the purification of common salt. See, in common salt, NaCl solid, we prepare its is a saturated solution. So when we prepare saturated solution of NaCl and we pass HCl through it. So see, this is a common ion. The NaCl is a strong electrolyte, but when it is in saturated solution, then insoluble NaCl is in equilibrium with soluble NaCl, because here we are making its a saturated solution along with impurities. So when HCl is passed through it, this equilibrium shifts backward due to common ion effect, and that's why what happened, we get pure NaCl. Now next is concentration of sulfide ion in the group 2 and group 4 analysis of cations is controlled by HCl and NH4OH. See, what are group reagent for group 2? It is H2S in the presence of it is HCl in the presence of H2S, right? HCl we pass H2S through the solution where HCl is already added. So this is group reagent for group 2. And in group 4, what do we do? We add NH4Cl, NH4OH, and then pass H2S gas through it. And in both the cases, we get sulfides. This is practical part. Practicals mein we have done this. So what happened to first tell me, which group will get more sulfide ions? Group 2 or group 4? किस केस में मोर सल्फाइड आयंस होंगे? हेलो, सल्फाइड आयंस किस केस में ज्यादा होंगे? Yes, because in group 2 you have 2H plus sulfide ion, and HCl will give H plus and Cl negative, and therefore there is common ion effect. So equilibrium shifts backward. So that means group 2 need less number of sulfide ion. That means its solubility is less. Solubility product of group 2 is less than solubility product of group 4. That's why we need less number of sulfide ions. Therefore, for the safe side, we add HCl. If by chance we forget to add HCl and we pass H2S gas, then we get sulfide ions of group 2 as well as group 4. But in the presence of HCl, when we pass H2S gas, then we get only sulfides of group 2. And in this case, in the another case, H2S, we add NH4OH. Obviously, it is also weak base, but there is odd ion effect. And due to odd ion effect, equilibrium shifts somewhat forward, and therefore we get more number of sulfide ions, and therefore now group 4 radicals get precipitated as sulfide. So this is also the application of a common ion effect. Now hydrolysis of salts. So the process of interaction between water and cation or anion or both of the salt give acidic, basic or neutral solutions, and that is called salt hydrolysis. And you know, when acid and base react, they give salt and water. So this is reverse of neutralization, and salt is formed by the union of a cation and anion, and this cation or anion may, when combined, they may be simple or complex ions. So there are different types of hydrolysis. First is salt of a strong acid and strong base, salt of a strong acid and weak base, salt of a strong base and weak acid, salt of weak base and weak acid. So first, salt of strong acid and strong base. For example, chlorides, sulfates, nitrates, perchlorates. See, to give HCl, H2SO4, HNO3, HClO4, they are all strong acids. And alkali metal salts like KOH, NaOH and so on, they are all strong base. Such salt cannot be hydrolyzed. Their pH is always 7. But salt of strong acid and weak base, so generally first members of alkaline earth metals, other group metal are hydroxides with strong acids like say ammonium chloride, ammonium salts are, you know, ammonium hydroxide is a weak base. Same CuOH twice, weak base. AlOH thrice, weak base. Zinc hydroxide, weak base. Magnesium hydroxide, again weak base. Even calcium hydroxide is also a weak base. So these are weak bases, and again there are nitric acid, perchloric acid, sulfuric acid, they are strong acids. Salt of strong base and weak acid. So obviously there are most of the alkali metals which form strong bases, and H2C2O4, that is oxalic acid, acetic acid, carbonic acid, H2S, HNO2, HF, HCN, H3PO4, H2SO3, they are weak acids. Salt of strong base and weak acid we have covered. Then salt of weak, both weak. So see, acetic acid, ammonium hydroxide, formic acid, ammonium hydroxide, all are weak acid and weak base. So in case of salt of weak acid and weak base, if Ka and Kb are equal, then solution is exactly neutral. But if Ka is slightly greater than Kb, solution is acidic, like ammonium formate. If Ka is less than Kb, solution is basic, because Kb of magnesium hydroxide is greater than Ka of HCN. So first I told you, salt of strong acid and strong base cannot be hydrolyzed. They are only, these ions are hydrated, because acid and base produced, they are strong and therefore they completely ionize in water. and H plus ion concentration is equal to OH negative ion concentration. Therefore, it remains neutral. Its pH is always 7. So there is no salt hydrolysis. So ऐसा अगर क्वेश्चन आए कि which salt is not hydrolyzed, so you will look at the cations and anions. Those cations and anions should form strong acid and strong base. Reverse, it is reverse of neutralization, that is salt hydrolysis. See, this is neutralization and this is salt hydrolysis. So Na plus, you know, it form strong base. So Na plus cannot be hydrolyzed because Na plus gives it completely ionized into Na plus and OH negative. Therefore, it is not hydrolyzed, but it is hydrated. There are water surrounding it. Same chloride ion, you know, chloride give HCl, strong acid. It is also not hydrolyzed. It is again hydrated. OH negative, like we have NaOH. So Na plus as well as OH negative, both are hydrated. Again, cations like this of strong base and anions like these all are strong acids. So they get simply hydrated but do not undergo hydrolysis. So which type of salts undergo salt hydrolysis? So these are 3. At least one should be weak. Salt of strong base, weak acid, salt of strong acid, weak base, or both weak. But if it is a salt of strong acid and strong base, that cannot be hydrolyzed. Now hydrolysis of salt of strong acid and weak base like ammonium chloride. So when ammonium chloride is hydrolyzed, we get ammonium hydroxide, which is a weak base, and HCl, which is a strong acid. So as one of them is weak, therefore it can be hydrolyzed, and obviously as acid is strong, so H plus concentration is greater than OH negative concentration, and pH of the solution is less than 7, and obviously it turns blue litmus to red. Solution remains colorless by the addition of phenolphthalein, because you know phenolphthalein is a weak acid. So all the indicators are either weak acid or weak bases. So see, this is the relation. Unionized indicator, ionized indicator. Unionized indicator is colorless. Phenolphthalein in unionized form is colorless, and in ionized form it is pink. So in acidic medium, what happened? When we add HCl, we have H plus ion in excess, and due to common ion effect, equilibrium shifts backward, and therefore dominating species in the solution is unionized phenolphthalein, and therefore it is colorless. But if we add base, so there is an odd ion effect, this is common ion effect. If we add base like NaOH, then H plus ions are neutralized by OH negative, equilibrium shifts forward. So then ionized form is in excess. Ionized form is dominating, and therefore the solution becomes pink in color. Again, methyl orange indicator. So methyl orange indicator is a weak base. So reverse happened in this case. So solution exhibits acidic character when H plus ions are greater than OH negative, and it is which type of hydrolysis? Cationic hydrolysis, because only cationic part is undergoing hydrolysis, and therefore it is acidic in nature. Degree of hydrolysis, just like weak acid and weak base, alpha was under root Ka upon C. Here instead of Ka and Kb we have Kh, that is hydrolysis constant. So H is equal to square root of Kh upon C, and Kh is equal to Kw upon Kb, weak part, because only weak part undergoes hydrolysis. So it is a weak base, therefore we take into account Kb. So Kh equal to Kw upon Kb, or H is equal to Kw square root of Kw upon Kb into C. H plus ion concentration, that is C into H, and therefore H plus is square root of Kw into C upon Kb, and pH is, see in this case pH is less than 7, right, because solution is acidic. So pH is equal to 7 minus half pKa plus log C, minus 7 minus half of pKa plus log C. If we have weak acid, so in this case again H is same, under root Kh upon C. So what is Kh here? Kw upon Ka. In case of weak base it was Kw upon Kb. If it is weak acid, then it is Kw upon Ka. And here pH was 7 minus half of pKb plus log C. In this case it becomes 7 plus half pK plus log C. See. Here OH negative ions are more, pH is greater than 7, it turns red litmus to blue. Again same color combination of phenolphthalein and methyl orange, and here anion part undergoes hydrolysis, and therefore it is called anionic hydrolysis. C, again H is square root of Kh upon C, Kh equal to Kw upon Ka. Instead of Kw upon Kb, now it is Kw upon Ka. So H is square root of Kw upon Ka into C. Now in the other case it was H plus ion is equal to Ch. Here it is OH negative ion equal to Ch. So OH negative ion concentration is equal to square root of Kw into C upon Ka. So see POH 7, pH is equal to 7 plus half pKa plus log C. Means it is pH equal to 7 plus half pKa plus log C. If both are weak, so if both are weak, then what happened? Now Kh equal to Kw upon Ka into Kb. Now Kh equal to Kw upon Ka into Kb, because both are weak. And here H is equal to square root of Kh, means C is not appearing. It is independent of concentration. Degree of hydrolysis is independent of concentration. This is important. For weak acid and weak base, degree of dissociation as well as pH is independent of concentration. It depends upon Ka and Kb only. See, Kh equal to square root of Kw upon Ka into Kb. H is equal to square root of Kw upon Ka into Kb. And pH, in this case, it is 7 plus half pKa minus pKb. So pH is also independent of the initial concentration. So see, I write it first. If it is salt of strong base and weak acid. So what is pH? Obviously strong base will decide. pH is greater than 7 and pH is equal to 7 plus half pKa plus log C. If it is salt of weak base and strong acid, obviously pH is less than 7. So in this case, pH is equal to 7 minus half of pKb plus log C. If both are weak, then pH equal to 7 plus half of pKa minus pKb. 7 plus half of, see, pK is plus, pKb is minus. So that's it. It is 7 plus half pKa minus pKb. This one is most important. It is also given in NCERT. Okay, in weak acid, weak base, actually it depends upon Ka and Kb. If Ka is equal to Kb, like in ammonium acetate, in that case pH is equal to 7 only, means solution is neutral, nearly neutral. But if Ka is greater than Kb, pH is slightly less than 7 and it becomes acidic, because Ka less than Kb means pKa is less than pKb. So pH becomes less than 7. If Ka is less than Kb, means pKa is greater than pKb, then pH, in this case pH is less than 7. In this case pH is greater than 7, slightly greater than slightly, means it is nearly neutral. But if Ka equal to Kb, then it is 7. If it can be less than 7, slightly less than 7 or slightly greater than 7, depending upon strength or dissociation constants of acid and base. If base is strong, if acid is strong, then pH is less than 7, because Ka greater than Kb means acid strength is more than base strength. If Ka less than means acid strength is less, means base is dominating. Base will decide the nature. So it is basic, pH is greater than 7. Now amphiprotic means like these salts. Amphiprotic means which can accept H plus ion as well as can donate, just like ambidentate nucleophiles. Amphiprotic means which can give H plus ion or accept. It can act as acid as well as base. So see, H3PO4, it only can donate H plus. So H3PO4 is an acid, but H2PO4 is amphiprotic anion. It can accept H plus, it can donate H plus. So first H plus ion given, that is Ka1. To give second, it is Ka2. To give third, it is Ka3. So H3PO4 is a triprotic, or we can say polyprotic acid. So H2PO4. Yes, beta. Zwitterion. Actually, zwitterion means which can have acidic as well as basic groups in the same molecule. So that is called zwitterion. Okay. Here it cannot be because it has not two groups. It is simply one which can accept or donate. Like you are talking about amino acids, like, see, in this case there is basic group as well as acidic group. Both the groups are in the same molecule. So H plus ion is donated by one group and accepted by the other group. There are two functional groups in the same molecule. That is called zwitterion. Okay. In this case, see, we have H2PO4 negative. So it can accept or donate H plus. So this is, we cannot call it as zwitterion. Okay. So H3PO4 is a triprotic or polyprotic acid. So these two are amphiprotic anions. So if we have H2PO4 negative, that is the first equivalence point, all the H3PO4 is converted into H2PO4 negative, then at that time pH is equal to pKa1 plus pKa2 divided by 2. Second, HPO4 2 negative. So H2PO4 negative, it can give HPO4 2 negative or H3PO4. So here it is Ka1, Ka2. So we take into account pK1 plus pK2 divided by 2. This is first equivalence point. Now second, if we have HPO4 2 negative, it can give PO4 3 negative, that is Ka3, or H2 PO4 negative, that is Ka2. So pH for HPO4 2 negative, that is equal to HPO4 pKa2 plus pKa3 divided by 2. For HCO3 1 negative in aqueous solution, again it is pKa1 and pKa2. Right? So this is also important part. This is second equivalence point. Sorry. What is pH of a salt? Sodium acetate. So you know sodium acetate, it is like this. It is a salt of weak acid and a strong base. pKa is given to us. So what was pH? Its pH should be greater than 7 and pH is equal to 7 plus half pKa plus log C. So see, pH equal to half pKa, that is 4.7, and log C, so C is 0.1. So log of 10 raised power minus 1, that is minus 1 only. And minus 1 into half. so minus 0.5. So pH comes out to be 8.85. Hydrolysis constant. What is the value of hydrolysis constant of a salt of weak acid and weak base? So hydrolysis constant was, both are weak, so Kw divided by Ka into Kb. pH of weak acid, weak base. So what was its pH? 7 plus half pKa minus pKb. So here see, value of Ka and Kb is same. So if value, there is no need to do all the calculations, because if Ka value is same as Kb, pKa is equal to pKb, and therefore pH is 7 only. So here no need to calculate it. Okay, buffer solution. The solution which resists the change in pH on dilution or on addition of small amount of acid or alkali, that is called buffer solution. And its practically its nature is what is its pH, resist in pH, that is its basic nature. Buffer is used to resist the change in its pH on adding small amount of acid or base, like blood has buffer solution, right? What was the composition of buffer of blood? It is H2CO3, HCO3 negative. Buffer maintains pH by removing the base added by the buffer action, or alkalinity means removal of acid added. So buffer has a reserve acidity or a reserve basic alkalinity. So buffers solutions on the basis of pH value, they are either acidic buffer solution or basic buffer solution. They are called mixed buffer. So acidic buffer means which consists of weak acid and its salt with a strong base, like we have acetic acid along with sodium acetate. Okay. Next is acetic acid, sodium acetate, or this blood buffer H2CO3 and NaHCO3. Even tetraboric acid H2B4O7 and Na2B4O7, H3PO4, NaH2PO4, HCN, KCN, they are all examples of acidic buffer. Basic buffer means it consists of weak base and its salt with strong acid. Ammonium hydroxide and ammonium chloride, glycine and glycine hydrochloride, then glycine NH2CH2COH, you know, and NH2CH2COH dot HCl. So see, pH versus H3O plus or OH negative. If we add more acid, see, from this is the buffer range. If we add, say, small amount of acid and base, it can means counter. But if we add excess of acid or base, then pH will decrease drastically. here same, this is the buffer range where there is a decrease or increase in pH to small extent, but if we add more base or more acid, then it will not show its action. Other types are means a mixture of acid salt and a normal salt. Na2CO3, NaHCO3, both are salt. Phosphoric acid, tribasic acid, so Na3PO4, Na2HPO4, they are also buffer. Salt of both weak acid and weak base, they also behave as buffer. Ammonium acetate, ammonium formate, ammonium oxalate. Ampholites or amphoteric electrolytes, they can show both properties of acids as well as base, like proteins and amino acid act as ampholites. See, glycine, alanine, glutamic acid. So how do buffer act? Let us say we have this buffer, acidic buffer. Now we add acid, sodium acetate, okay. Strong acid is added to it. Let us say we add few drops of HCl to the buffer solution. So what happened? You know, it will give H plus ions. Now the solution has acetic acid. So when HCl is added, due to common ion effect, this equilibrium shifts backward. So that will decrease the small amount of H plus ions added from our side, and therefore it tried to change the pH, but buffer should remove these H plus ions to maintain the pH like this. In this way, unionized acetic acid becomes more, and H plus ions which are added by us, they are removed by the buffer. This is called buffer action. So buffer maintains the pH of the, as the acetate ion which are in large proportion, they react with added H plus ion and therefore removes them as feebly ionized acetic acid is formed. Same if we add sodium hydroxide to the buffer solution. So now OH negative ions are more. So when OH negative ions are more, then what happened? Acetic acid, again, which is a weak acid, that OH negative ion added, what they do? They will ionize it. They will ionize acetic acid, and therefore in this way they remove OH negative. So in this way buffer maintains pH by removing both added H plus or OH negative ion of the acid or base. Same is the action of basic buffer. So these are the relation for acidic buffer: pH equal to pKa minus log of salt, acid over salt, or this is the expression, this is great, pH equal to pKa plus log salt over acid. Salt means conjugate base concentration, and for basic buffer it is POH, that is equal to pKb plus log salt over base, or pH plus POH equal to 14, or pH equal to 14 minus POH. So pH equal to 14 minus pKb minus log of salt over base. Buffer capacity. So buffer capacity is when we add acid or base, how much it resists the change in pH. That is called buffer capacity. That means it is the number of moles of acid or base added to 1 liter of buffer solution to cause the change in pH by 1 unit, or we can write it like this: number of moles of acid or base added divided by change in pH. This is the amount of or moles of acid or base added divided by change in pH, and that is called buffer capacity. pH range of a buffer. So it is a range of pH where buffer can effectively resist the change in pH on adding acid or base. So for acidic buffer it is pKa plus minus 1. For basic buffer it is pKb plus minus 1. See, for basic buffer it is pKb plus minus 1, or 14 minus pOH, that is pKb plus minus 1. 14 minus pKb plus minus 1. So see, so for basic buffer, for acidic buffer pH equal to pKa plus minus 1. For basic buffer pOH equal to pKb plus minus 1. So buffer capacity is maximum when pH equal to pK. If pH is equal to pKa, that is if acid and salt are equal, that is called, that has maximum buffer capacity. That buffer has maximum buffer capacity. So buffer concentration will be higher if component concentration is higher. Any buffer has a definite pH value. pH of buffer solution does not change on long standing. If we kept it stored, pH does not change, and pH of buffer solution does not change on dilution even. So it is used in chemical industry, enzyme catalysis, softening of hard water, even various research programs. Means buffer is very, very important even in chemical analysis. Buffers are used to determine pH with the help of indicators. Normal pH of blood is 7.4. It is maintained by two buffers: carbonic acid buffer, that is most common, H2CO3 and NaHCO3, and phosphoric acid buffer, that is H2PO4 negative and HPO4 2 negative. In gravimetric analysis, to precipitate lead chromate, acetic acid buffer is used. Acetic acid plus sodium acetate, this buffer is used for the gravimetric precipitation of lead chromate. In qualitative analysis of group 3, in group 3 we are using ammonium hydroxide and ammonium chloride. So that is also a buffer solution, and here it is group 3 elements are precipitated in the form of hydroxides. Ammonium chloride, ammonium hydroxide, ammonium carbonate, they are used in the precipitation of group 5 cations as carbonates. So pH of a buffer solution is 4.745. If we add 0.01 mole of NaOH to 1 liter of it, pH changes to 4.832. So what is the buffer capacity? So you know buffer capacity is number of moles of acid or base added divided by change in pH. So pH change is 4.832 minus 4.745. So it comes out to be 0.087, and how many moles of NaOH are added? 0.01. So it comes out to be 0.115. That is the buffer capacity of a buffer solution. तो शाम को आपके पास टाइम होगा बच्चे? आप फ्री हो शाम को ऐसा? 6 o'clock से क्लास है अप टू 6. 6 to 6:30 onwards you are free, or before it? Okay, 6:30 onwards free. Okay, 6:30 to 8. That is it possible to have class at 5 o'clock? Okay, so I will be online at 5 o'clock to finish this off, because only one topic is left, that is solubility product and few questions. Right? Okay. Bye. Welcome. Bye. Okay, so am I? सूर्यवंशी रजत 11th में पढ़ा था. Okay, Rajat. So now you are preparing for what? Yes, Rajat. अभी किसके लिए प्रिपेयर कर रहे हो आप? Okay.